Hello everyone, I'm Soheila, a research associate at University of Cambridge. The title of my review paper is Exploring Deep Generative Models in Building Design. Generative design is an iterative process that generates a wide range of designs considering constraints and objectives. There are three main components for generative design, including exploration that explores the entire design space for generating a wide range of designs, iteration that is useful for rapid exploration, and optimization for finding optimal solutions. The typical components of design problems using deep generative models are design task, representation method, generative model, functional performance modeling, and synthesis output. Deep generative models typically control deep networks to learn from an input data set for creating new design. And there are three main algorithms for the deep generative models, including generative adversarial network, variational autoencoders, and deep reinforcement learning. And these algorithms can be used separately or in combination. This algorithm can generate and design diverse architectural and structural elements, including facades, interior layouts, building masses, and floor plans. One efficient algorithm is generative adversarial network, which is based on deep learning model, and it has two main components, generator and discriminator. The generator can generate new design, and the discriminator learns to distinguish between real and fake data. This is an example of using generative adversarial network for designing the floor plan, and in this figure you can see the floor plan designing workflow with house GAN. And the input to the system is a bubble diagram encoding high-level architectural constraints, and house GAN learns to generate a diverse set of layouts, and after that architect can convert those layouts to the real plans. This figure shows the comprehensive analysis of failure and success instances. And as you can see in the first one, the problem is that the balcony is only accessible through bathrooms. The problem for the second one is that a closet is situated within a kitchen, and also kitchen being divided into two separated spaces. This is another example of using GAN. So in this study, an attention-enhanced generative adversarial network is proposed for the layout design of the shear walls. In this study, a pre-training method is introduced to overcome the data shortage, and the result presents the better structural performance and lesser material consumption. In the case of generative design for steel structures, I prepared an example of tree-like column structures. So the first one is the Stuttgart Airport, the second one is the National Gallery in Singapore, the third one is the shopping center in London, and the last one is Shanghai Pudong Airport. This figure shows the details of this kind of joint. And in this study, they use the integration of generative design and additive manufacturing. So they generate hundreds of models by generative design using a cloud computing platform. And after that, they selected two samples with the lowest mass for further analysis. And then they use topology optimization for finding the optimal solution. This is also another study that uses GAN for generating high-rise building sketches with user preferences, considering two criteria, shape preferences and architectural fusion. So the shape preference module with self-space GAN lets users draw a simple sketch to decide the shape of the building, and the self-similarity score is proposed to obtain the degree of similarity. And for the second criteria, the architectural fusion module allows to implement user preference elements by using the line loss with a feature-based attention mechanism. Another efficient method is variational autoencoder, and autoencoders are unsupervised algorithm, and it has two main components, encoder and decoder. Encoder that maps an input data to a lower dimensional latent space, and decoder that reconstructs the design as accurately as possible from the latent space. And the encoder and decoder are implemented using deep neural networks. This is another example of generative design using variational autoencoder for designing long span roof structures. So in this study, a complex design space is converted to the continuous, smooth, and low dimensional space. And this latent space can be explored by designers since it offers a diversity of high-performing design options. This is also another example of using variational autoencoders. So in this study, variational autoencoders are utilized to generate topological variation of shell structure forms. And in the figure on the left, you can see the stages involved in the conversion of a 2D depth map into a 3D mesh. And in the next figure, you can see the representation of Pareto optimal solution in the objective space. And in the right figure, you can see the perspective view of the selected design and their footprints. Another deep generative model is reinforcement learning. So reinforcement learning learns without a data set in an unsupervised approach by a large set of trial and error interaction between an actor and an environment. This is usually done by some reward signal being sent to the actor after taking action. And in this scenario, the actor's goal is to maximize the rewards that it receives by making decisions. In this study, an algorithm is introduced that combines reinforcement learning with off-policy Monte Carlo tree search for generative floor plan designs. And this matrix shows the constraints for this design. The value 1 shows that 2 rooms should be adjacent. The value -1 shows that those 2 rooms shouldn't be next to each other. And the value 0 shows that there is no constraint between those 2 rooms. So the rooms placed from top right to the bottom left using this algorithm. And as you can see in this figure, room 2, 3, 5, 1, and 4 are placed in sequence within the boundary of the building. The simulation result is then evaluated against the user input constraint matrix to produce a reward. And after multiple simulation, the best next action is conducted and the next time step starts. And the process proceeds until all rooms have been placed in the right place. This is also another example of using reinforcement learning. So in this study, a reinforcement learning-based method is presented for automated reinforcement concrete beam design. This method is based on the deep deterministic policy gradient and convolutional neural network function approximators. And they demonstrated that the reinforcement learning agent can successfully create continuous beam members with design quality comparable to optimized design without requiring an iterative process. Also, an important thing is to clearly define the collection of reward function to get the best results. As a part of reusor project, which is reuse of structural steel in construction, I developed a generative design platform that can generate different variation of warehouse structures with different dimensions. After that, we have a collection of scanned beams that can be reused. And then I used matching algorithm to match the required elements with the elements that can be reused. The strengths of GAN method are high quality generation, diversity in generation, and unsupervised learning. However, the weakness are mode collapse, training instability, and evaluation matrix. The strengths of variational autoencoders are continuous latent space, structure, representation learning, and application in dimensionality reduction. However, the weakness are blue regeneration, difficulty in capturing shape features, and sensitivity to hyperparameters. The strengths of reinforcement learning are flexible framework, learning complex policies, and sample efficiency. However, the weakness are sample complexity, reward design, and partial observability challenges. In general, challenges and limitations of all of these deep generative models are computational complexity, assessment of design efficiency, interpretability, and creating innovative and original ideas. And these challenges can be overcome by quantum computing, enhancing models, explainability methods, and using language models. Thank you.